Okay, so this is the second half of the condensed review of everything relating to organic chemistry. And I'm just going to pick up where I left off in the problems at the end of part 1. Again, you will need your reference tables P, Q, and R. As I go through these different problems, I will be referring to these tables. Which Lewis dot diagram represents chloroethene? So the first thing that we want to do is dissect the name. The ene, the ene ending, tells us from table Q that there is a double bond. Remember that anything that ends in A is single bonds, ene has a double bond, and ine has a triple bond. And you don't have to memorize this. This is table Q. So I'm looking for a double bond. 4 is out, 2 is out. So here I see I've got a double bond in the middle here. Let's get a highlighter. And there's a double bond here. Now let's see what's going on. The problem with this diagram over on the right is that there's too many electrons here. Remember, carbon forms 4 bonds but can only have a total of 8 electrons. 2, 4, 6, 8, 10. This C alone has 10 electrons. 2, 4, 6, 8, 10. This C has 10 electrons. That's way too many. Here 2, 4, 6, 8. That one's good. 2, 4, 6, 8. That one's good. So there's our answer. Which class of organic compounds? As soon as you see class of organic compounds, you're going to table R. There is a column that says class of organic compounds. And it has to contain nitrogen. So let's go to table R. Here's our class of organic compounds. So they're looking for one of these. And we're looking for nitrogen. Well, 2 of them contain nitrogen, amines and amides. So let's go back to our question. And only the amine is listed, so there's our answer. Given a formula of functional group, they want to know what this is classified as. So you're looking for the COOH. Again, we're going to table R. And I'm looking down my functional groups. That's COOH. Nope. COOH. There it is. It's an organic acid. So I go back to my question. And it's an acid. Next question. Given the structural formula for 2 compounds, one on the left and one on the right, the difference in their physical and chemical properties are primarily due to what? Well, let's see what we have going on here. I got 4 C's, 8 H's, and 2 O's. And over here, I have 4 C's, 8 H's, and 2 O's. So right away we know that they have the same molecular formula, which means they're going to have the same mass because they have the same number of carbon, hydrogens, and oxygens. They have the same number of carbons. They have the same number of hydrogens. So functional group. Their functional groups are different. COOH is an acid and COO is an ester. And we can look at these right in table R. Which structural formula represents an alcohol? So if I go to my reference table and I look up alcohol, I see that the functional group is OH, and it's usually on the end. Go back to my question. I'm looking for OH, Here it is right here on number 3. Just to review, a double bonded oxygen in the middle of a chain is a ketone. A double bonded oxygen on an end carbon is an aldehyde. And your COOH ending is your organic acid. One more thing before I leave. Often students, when the OH is written on the other end, don't recognize it as an alcohol. So let me explain this. These two diagrams, choice 2 and the one I just drew, are exactly the same molecule. They are both propanol because it's 3 carbons and they have an OH group. When the OH is written on the right, it's written as OH because remember, I'm going to draw this right down here, O has to form 2 bonds. So it's forming one with the C on the left and one with the H on the right. Same over here, oxygen has to form 2 bonds, so it has to be written HO. If I tried to write OH on the left like I did on the right, then I'd be saying H is forming 2 bonds and oxygen is only forming 1, and that can't happen. So these are synonymous. This one is synonymous with this one. They're mirror images. Molecules of 1 bromopropane and 2 bromopropane differ in what? Well, they're both got 3 carbons, they're both single bonds, they both have a bromine, and the only difference is that the bromine is on the first carbon in this one and in the second carbon on the second structure. So they have the same molecular formula, the same number of carbons, and the same number of bromines. They differ in their structural formula. Given the 3 organic structures shown below, which organic compound classes are represented by these structural formulas from left to right? So I have a double bonded oxygen on an interior carbon. This is a ketone. I'm going to show you this in table R in a minute. Here I have a COOH ending. This is an organic acid. And I have an OH group on this one, so that is an alcohol. So let's go to table R and take a look at that real quick. Alcohol, there's your OH ending. Here it is in your example. Organic acid, the COOH ending. Here it is in an example. And a ketone, a double bonded oxygen, but it's easier to see in the example. See how the double bond is on an interior carbon, whereas an aldehyde, it's always on an end. The compounds 2-butanol and 2-butene both contain. Well, first of all, but means 4 carbons. So they both have 4 carbons. So there's your answer right there. Double bonds is only located in the butene because it ends in ene. Single bonds would be in butanol. And they don't have the same number of oxygens because butene is a hydrocarbon and doesn't have any oxygens because it's in table Q. Ethanol and dimethyl ether. So ethanol is 2 carbons. Eth tells us that. The OL tells us it has an OH ending. And then remember the rest of these are H's because each C has to have 4 bonds. Dimethyl ether. So an ether has an O. Dimethyl means 2, and methyl means C's. So it has 2 C's, one on either side of the O. So they don't have the same functional group. So that is how they are different. So that's choice 1. They have the same molecular mass because they both have 2 C's, 6 H's, and 1 O. 2 C's, 6 H's, and 1 O. So they have the same molecular mass, they have the same number of covalent bonds, and they're going to have the same percent composition by mass because they have the same numbers of atoms of each kind of element. So let's see what's going on here. I have an NH2 group, and I have a COOH group. So let's go to table R. Here's my COOH group, which means an organic acid, and here's my NH2. It's kind of hard to see the H's here, but you can see an example. So I have an amine and an organic acid. So if I put the two of those together, I get amino acid. All right. Draw the structure for the product 1,2-dichlorobutane. Let's take this apart. Table P tells us that the but is 4 C's. Table Q tells us that the ANE is all single bonds. And di means 2, chloro means Cl. So I have 2 chlorines, and they're positioned at the number 1 and number 2 carbon. So let's draw 4 C's. Off the first one, I've got a Cl. Off the second one, I've got a Cl. I could have put in this Cl anywhere on this end carbon. And the rest of these are H's, because each C has to form 4 bonds. Thiol is very similar to an alcohol, but thiol has a sulfur atom instead of an oxygen atom. So alcohol is OH, and thiol has an S instead of an O. So explain in terms of composition why this is a thiol. Well, it's because it has an SH. Functional group. You could probably just write it as an SH, and you're going to get credit. All right. Moving right along here, an unlit candle is secured to the bottom of a 200 milliliter glass beaker. Baking soda, which is sodium hydrogen carbonate, is added around the base. The candle is lit, and dilute ethanoic acid, that's important, is poured down the inside of the beaker. As the acid reacts with the baking soda, bubbles of CO2 gas form. After a few seconds, the air in the beaker is replaced by 0.2 liters of CO2 gas, causing the candle flame to go out. The density of the CO2 is 1.8 grams per liter. Wow. Draw the structural formula for the acid. So all that, because they want me to go back and draw ethanoic acid. Nice. I could have skipped all that reading. So, an acid refers to organic acid, so it has to have the functional group C double bond O OH. And I'll show you that in table R. Eth means 2 C's. There's my double bond O OH. And then each C has to have 4 bonds. So I need 3 H's here. 1, 2, 3, 4. This one's good. So that's my structure. Let's go to table R. Organic acid, C double bond O OH. And here, look at the example. The example was propanoic. Prop means 3 carbons. So all you have to do is shorten this to 2 carbons, and then make sure that you have enough H's on that N carbon, that it has 4 bonds, which is what I did here. Okay, moving along. Glycine, NH2CH2COOH, is an organic compound found in proteins. Acetamide, CH3CONH2, is an organic compound that is excellent solvent. Both glycine and acetamide consist of the same 4 elements, but the compounds have a different functional group. Identify one functional group in the glycine molecule. So the biggest one that's easy to see is the COOH, and the other one that's here is the NH2. So this glycine is actually an amino acid because it has an amine group and it has the COOH. So either one of these could be listed. So you could put, you could put COOH as an answer or NH2, either one. Okay. So in this one, I'm going to skip all the reading. I'm just going to see what they want me to do for the sake of time. Draw the structural formula for acetamide. So this is acetamide. Again, break it up where your C's are. So I'm going to draw CH3. Then I'm going to draw a C. And then I'm going to draw an O and NH3. So this is where students get confused. Okay, I'm going to show you what to do, but I know that oxygen forms a double bond, so it goes here, and nitrogen forms 3 bonds, so one of them has to be with the C, and then the other 2 are H's. So that is acetamide. Let's go back to table R and see what to do here. So acetamide is an amide, and you can see right here by looking at the functional group that the O has to be a double bond and then your NH2. And actually, here is propanamide. So all you had to do is make sure that the ending looked just like this one. Okay? Alright, moving on. Given the ester ethyl butanoate, in the space provided on a separate piece of paper, draw the structural formula for this ester. Determine the gram formula mass. Alright, I'm going to do this at the bottom. Esters are tricky, but I am going to use the example in table R to show you how to answer this question first. Because if I show you how to use the example in table R, you can then apply it to any ester that you're given. So let's go to table R, erase. Alright, so let's look at the ester that we have here. What you're going to do is you are always going to use this O right here as the dividing line. That O. Okay? Notice it starts with methyl. Methyl means 1 carbon. If this O is your dividing line, the only place you see 1 carbon is at the end. Propanoate. Prop means 3 carbons. If you look to the left of the O, this dividing line, you see 1, 2, 3 carbons. So this is the key to drawing any ester. The first part of the name is drawn last after the O, and the last part of the name is drawn first before the O, with the functional group being the COO. Now, notice that this C is to the left of the O, so it is part of that string to the left, so the prop. So let me go back to our question. So I need to draw ethyl butanoate. So remember, my functional group, well, first of all, my O is my dividing line, right? So I'm just going to draw my O first. The ethyl was named first, but it's the number of C's after the O. So I'm going to put 2 C's. The bute is named last, but refers to the C's before the O. Bute from table P is 4 C's. The rest of my functional group, when I look at it, has a double bonded oxygen off of this C. And then I just have to put in my H's. This one's got 4, 1, 2, 3, 4. Oxygen only gets 2 bonds. This C has 4, 1, 2, 3, 4. This C now has 4. This C now has 4. And now that C has 4. So that is ethyl, named first, and, oops, let me highlight this. Drawn last, and butanoate, named last, drawn first, the 4 C's. And then my functional group is in the middle. Here is my functional group. Alright, now what do they want? They want the gram formula mass of this. I've got 1, 2, 3, 4, 5. Got 5 C's. So it's 5 times 12, which is going to be 60. And I've got 2 O's times 18, which is 36. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 H's times 1, which is 12. So 108 grams. There you go. Alright, on a separate piece of paper, draw the structural formula for butanoic acid. First thing that I'm going to do is go to table R. My acids have a COOH functional group. Here is propanoic. Propanoic has 3 carbons. I want butanoic, which has 4. So all I'm going to do is draw my functional group and make sure that it has a total. This has a total of 3, has a total of 4 carbons. So I go back to my question. So I'm going to draw this down here, 21. So here's my functional group, C, double bond O, OH. And I need a total of 4 carbons, 1, 2, 3, 4. Make sure I have all my H's, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and this one's good, 1, 1, 2, 3, 4. So there's butanoic acid. Can move this up a little. Alright, propanone. They want me to draw propanone. So go to table R. Propanone is a ketone. Propanone is a ketone, ends in O-N-E. You can just take the name and follow it in your examples. So this is pentanone, 1, 2, 3, 4, 5 C's, and this is 2-pentanone because it's telling you that the oxygen is on the second carbon. I just need propanone, 3 carbons, and in the ketone, remember, your double bonded oxygen has to be on an interior carbon. So prop, 1, 2, 3, double bonded oxygen. It's got to be on an interior carbon, otherwise it would be an aldehyde. So for that reason, in order to make a ketone, you need a minimum of 3 carbons, because otherwise you wouldn't have an interior carbon. All right, moving on. Let's see. Circle the acid functional group only. You can always pause and read all this stuff, but as you can see, we're finding that the most important information is actually right before the diagrams or at the end of the question. So it says circle the acid functional group. I think that you guys already know that the acid functional group is the COOH ending. Can match this up right on table R. The incomplete equation shown represents an esterification reaction. The alcohol reactant is represented by X. So this is the alcohol reactant. Write the UPAC name for the reactant represented by its structural formula in this equation. So this is the reactant that they show the structural formula for. They want the name of this. So right away I see the COOH functional group. I know it's an organic acid, and it contains 2 C's. 2 C's is F, so I just copy the ending, ethanoic acid. So let me go to table R. Oh, let me do the alcohol, and then I'll go to table R. It also says in the space provided, on a separate piece, draw the structural formula for the alcohol represented by X. So, ethanoic acid had 2 C's. Remember, this is your O is your dividing line in an ester. Here's your COO functional group, right? So we know it's an ester. So the dividing line is the O. The 2 C's before the O, that's this. It came from the acid, which means the 3 C's after the O came from the alcohol. So my alcohol has 3 C's, and an alcohol has an OH functional group. I'm going to show you that in table R, and then the rest of these are H's. So this was part A, and this was part B. So let's go back and look at table R. First of all, for the organic acid, notice this is propanoic. Prop has 3 C's. So we were dealing with ethanoic. So all you do is remove the prop and replace it with the prefix eth, and you have ethanoic. If I had 5 C's, I would remove the prop and put bute, and it would be butanoic, so on and so forth. And here is an alcohol. An alcohol has an OH functional group at the end, unless they tell us that the alcohol is somewhere else, the OH, and this was prop, so this is propanol. And you do the same thing. If it were butanol, we would take off the prop and replace it with bute. If it were pent, 5 carbons, we take off the prop and replace it with pent. Okay. So this is another ester question. This shows the reaction between butanoic acid and identified X. So here's but, 1, 2, 3, 4 C's, the C double O OH ending. So that's an acid. And this is an alcohol because the reaction between an alcohol and an ester is an alcohol and an acid forms an ester and water. So that's the esterification reaction. So what do they want us to do? They want us to draw X again. So here's my COO. That's my ester. My dividing line is my O. 1, 2, 3, 4. This came from the acid. There's my 4 C's. Here's my 4 C's. So my alcohol is what's after it. So this is 2 C's. 2 C's. And it's an alcohol, so it has to have the OH ending. And then these are just H's. So this is ethanol. All right. Write the UPAC name for the compound that reacts with vegetable oil to produce the biodiesel. So let's see. Biodiesel is an alternative fuel. For vehicles that uses petroleum diesel, biodiesel is produced by reacting vegetable oil with CH3OH. So that's what they want. They want the name for this compound that reacted with vegetable oil. So we go to table R. We know that the OH is an alcohol. There's only 1 C, so meth and all. So you just do the same thing. You remove from the example the prefix that's in table R, and you put your prefix for 1 carbon. And the class of organic compounds to which methyl palmitate belongs to. Go down your example list, the last column in table R, and see which one this matches up with. Methyl palmitate matches up with esters. Let's see. I'm going right here. Identify the functional group in a molecule of ethanol. OL, we know the functional group for alcohols is OH. Which compound is an isomer of pentane? Remember, isomer means same molecular formula. So the same number of C's, H's, O's, whatever's in it, and different structural arrangement. So the first thing that we need to know is what is the formula for pentane? Well, pent means 5, right? So you know it has 5 C's. And if you go to table Q, it ends in ANE, so it's all single bonds. So it follows the formula CnH2n plus 2. So if C is 5, 2 times 5 is 10, plus 2 is 12, so C5H12. That is the formula for pentane. Butane is going to have 1 less carbon. So 4. So this is going to be C4H10. Well, that's not it. Propane is going to be C3H8. That's not it. So now you have methylbutane and methylpropane. Well, prop is 3 carbons and meth is 1 carbon. So that's a total of 4 carbons. So you know that's not it. But is 4 carbons and meth is 1 carbon, so that's a total of 5 carbons. There's your winner. Your carbons match up. So I just want to show you, since I'm going to use this to teach you something else, I'm going to draw out pentane. So there's my C5H12. Methylbutane. But is 4 carbons. And it has a methyl group. So this is also C5H12. So they have the same molecular formula, but they have a different structural arrangement. Therefore, they have different chemical and physical properties, which is what makes them isomers. And in this next question, which ones are isomers? So I'm looking for the same molecular formula. So this is 1 C, 4 H's, and an O. This is 2 C's. Right off the bat, it's not that. This has each has a C, but this has H's, this has Cl's. Nope. This has got 1, 2 C's, 6 H's, and an O. And this has 1, 2, 3 C's. It's not that. 1, 2, 3 C's, 3, 4, 5, 6 H's, 1 O. 1, 2, 3 C's, 6 H's, 1 O. That matches up. Which formula is an isomer of butane? Well, you have to know what butane is first. But means 4, and ane is all single bonds. So it's going to be C4H10. So I'm looking for C4. This has a double bond. It can't be that because this doesn't have a double bond. 1, 2, 3 carbons. That doesn't match up. 1, 2, 3, 4 carbons. That matches up. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 H's. That matches up. And this has 1, 2, 3, 4, 5 carbons. That's definitely not it. Which two compounds have the same molecular formula but different chemical and physical properties? So they're talking about an isomer here. Again, Cl and Br, that's definitely not it. 1, 2, 3 C's, 6 H's, 3 C's, 6, 7, 8 H's. 1, 2, 2 C's, 4 H's and an O. 3 C's, nope. 2 C's, 6 H's and an O. 2 C's, 6 H's and an O. Last question here. The isomers, butane and methylpropane, differ in, well, we know it's structural formula because that's the definition of an isomer. Which formula represents an isomer of this compound? 1, 2, 3, 4. 4 C's, 3, 6, 7, 8, 8 H's, and 1 O. So, oh, and I have a double bond, so I want to make sure I keep that double bond, and a double bond. 1, 2, 3, 4 C's, 6, 7, 8 H's, 1 O, and a double bond. This is not an isomer. It's got the same molecular formula, it's got the same double bond. If I take this guy up here, my original, and flip it over, it is the mirror image of, number 1 is the mirror image of it. Mirror images do not count. 1, 2, 3, 4. 4 C's, 1, 2, 3, 4, 5, 6, 7, 8 H's. This has 2 O's though. This has 2 O's. 1, 2, 3, 4 C's, 8 H's, and an O, and a double bond. And it is not the mirror image of that, so there's my answer. Which structural formula represents a molecule that is not an isomer of pentane? Not. So pent is C5, ane is all single bonds, so again it fits the formula CN, H2N plus 2, so we need 12 hydrogens. 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. That's not it. 1, 2, 3, 4, 5. And we've got 4, 5, 6, 7, 8, 9, 10, 11, 12. This could be it. This is normal pentane. If I were to draw this out, that's not it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have two possibles. So let's see. Oh, this, I'm sorry. I just made a mistake. That's alright. It's getting late. This actually is an isomer because it's just a straight chain. So if I drew this one, C5H12, this would be an isomer of it. So this is also an isomer. These are isomers of one another. They all have the same molecular formula, but a different structural arrangement. This one is not an isomer because it is C5H10. I circled the knot, but I wasn't following my own directions. Alright, which two formulas represent compounds that are isomers? 1, 2, 3. 3 C's, H, 6, O. 3 C's, H, 6, O. But this has a double bond. This has a double bond. Okay. 3 C's, H, 6. This is O2. Can't be that one. C3. H. 8. O. Can't be that one. A and C. I got enough with the isomer questions. 1, 2, 3 C's, 8 H's, and an O. 1, 2, 3, 3 C's, 3, 4, 5, 6, 7, 8, 8 H's, 2 O's. BR. This has got 1 BR, this has got 2, not that. One, 2, 3 C's, 6 H's and an O. 1, 2, 3 C's, 6 H's and an O. 1, 2, 3 C's. That's 4 C's. All right. Molecules 2-methylbutane and 2,2-dimethylpropane have different what? So I can tell you right now, let's see, this is going to be 4 plus the methyl. 1 is 5 carbons. And this is going to be 3, 4, 5. So dimethyl means 2 carbons. So this is also going to be 2 plus 3 is 5 carbons. These guys are isomers, so they have different structural formulas. Draw an isomer of this. The easiest way to draw an isomer is to take a C off and put it somewhere in the middle. Do not put it on an end carbon because then you're just bending the chain and it's still one long line. So when you draw an isomer, you want to take it off and put it in the middle and then make sure everything's got all its H's. Each C has to form 4 bonds. Why there is no isomer of if I were to CH3OH. There we go. When butane burns an XX oxygen, the principal products are anytime something burns with oxygen, So you've got something plus O2. You're always going to get CO2 and water. This is a combustion reaction. So they're telling you butane. So butane is C4H10. So this guy's going to change. This could be butane, propane, methane. But if it burns in oxygen, they're always going to produce CO2 and water. Now, the amount of water and CO2 you get is going to differ because you're going to balance your equation based on what you're starting with. The process of joining many small molecules into larger molecules is called polymerization. Joining many, prefix for many is poly. So remember, a polymer is like a paperclip chain. Okay? We've all made paperclip chains. Each paperclip is a monomer. Mono meaning one unit. You link them together to make a polymer, many units. N. Whenever you see this N, it equals a very large number. So that's going to be a polymerization. Alright, let's see what we have going on here. COOH is an acid. The OH, or HO, because it's written on the left, is an alcohol. So we have an acid plus an alcohol. And then I have a COO functional group. COO, when we look in table R, is an ester and water. So the name ester tells you it's esterification. Alright, winding down with these reactions. Something plus Cl2 yields C2H5Cl plus HCl. Well, there's two specific reactions in organic chemistry. One is called addition and one is called substitution. Addition, you start with an unsaturated hydrocarbon, meaning a double or triple bond. You break it, put single bonds, and you add everything. Addition, add it all, so you only have one product. In substitution, you're taking something off, putting something on, and you wind up with two products. So, what happened here was this H came off of this molecule X and hooked up with one of these Cl's to make HCl. And the other Cl was put on the molecule. So my original molecule was C2H6. So I had C2, right, H6 plus Cl2. I took off one of these H's right there, and it hooked up with one of the Cl's, and then I put the other Cl where I took that H off, and that is substitution. I have to give up something to get something. Given the equation, X plus Cl2 yields XCl2, what compound can be represented by X? Notice the key to this is I have one product. Whatever I started with, I added it all. And the only way I can do that is if I start with an unsaturated hydrocarbon. So I need something with a double or a triple bond. And that's going to be this guy right here. It fits the formula CnH2n. So what you would do is go to table Q, plug in your number of C's, and see if it fits either the alkene or the alkyne formula. And that's your answer. The reaction that joins thousands of small identical molecules to one long molecule is called polymerization. Soap. You have to memorize. Soap is saponification. Saponification, if you slip that O in there, S-O-A-P, soap. So if you want to, it's saponification, but remember it as soaponification. All right, I'm getting punchy because I'm tired. The reaction between an organic acid and an alcohol produces an ester. That you kind of have to memorize. In the space to the right of the reactants and the arrow provided, draw the structural formula for the product. Starting with an unsaturated hydrocarbon, that means this is going to be addition. So I'm going to add it all. Easiest way to do this is to draw what I have. So I'm going to draw my 4 C's, but I'm going to change this to a single bond. I'm going to put all my H's back where they were. 1, 2, 3, 4. Okay. So when I break that double bond, look what it did. It opened up 2 bond sites, one here, one here. And that's where those 2 BRs fit right in. Oh my goodness. Let's see. What type of chemical reaction is represented by the equation? I have 2 products. I wind up with 1. C4H8 fits the formula for an alkene. Table Q, because my hydrogens are double my carbons, so this is addition. Identify the type of organic reaction shown. Br2 plus CH4. I have 2 products. I took off one of the H's because it went from 4 to 3. I added 1 Br, and the other Br hooked up with the H. So I had to give up something to get something. This is substitution. Enzymes. You have to know enzymes on activation energy. Enzymes decrease activation energy. We learned this in the kinetics and equilibrium unit. Remember, if I have a potential energy diagram, anytime I have a catalyst, it lowers the EA, which is the activation energy. And anything that ends in ASE is an enzyme. This is from like bio. And enzymes are biological catalysts. Type of reaction. 2 products. I got a double bond. Oh, it's breaking it. We just did this. This is addition. Added everything. Here, double bond, Br2. This is addition. What type of organic reaction? Organic reaction, COOH plus something yields COO. I go to table R. This is an acid plus a blank yields COO is an ester. So the reaction is not an ester, but it's esterification. And that is the end. So I hope you've enjoyed this review of organic chemistry. Good luck on your Regents.